Okay, so in the previous video we had looked at estimating a Cox-Ross-Rubinstein model using the efficient lattice search technique, which we made available in this paper here, an efficient lattice search on the SSRN website. Now it's possible to download that paper and get the VBA code. We use two snippets of VBA code from that paper. And then there is this highly efficient code, and then more static Cox-Ross-Rubinstein model code. Both yield the same results. So if we change this back to 3000, you can see the results are very fast, much faster than static code, while at the same time producing exactly the same results. Taken results from Brody and Temple, and then Schockelinghem and Murteraman, and so basically in each instance they provide results for binomial model. Here with Brody and the Temple from 1996 from Review Financial Studies, their table 1 sets out a number of different estimations. In fact, because it's like this, I have to rotate and copy and paste. I've already done that, and this is the table 1 here reproduced from Brody and the Temple. It has a maturity of 6 months, and we can run the estimations here using the faster code. So again, using the efficient lattice search approach, and we can compare the results between the true. Now I have the results here also, and maybe I can increase the magnitude, the amplification here, so that we can see a bit more clearly. But with a 50-step tree, the value for the American option using these parameter inputs would be 22 cents. It's different from the true value presented in table 1. However, in table 1, true, the final column, is considered to be true, and the true value is based on a binomial method with 15,000 time steps. Okay, so if we go back here and input in 15,000 steps, we can see how long it takes. It's not that slow, it's not too bad. We get 219. And that's consistent with 219 here. We can go again, 15,000, just to see, are we able to reproduce that level of accuracy? We do 1.386, consistent. We put in 15,000 again. Now 15,000 step tree is a relatively substantial tree, and it requires a huge amount of estimation. Typically it's n by n minus 1 divided by 2. Represent the number of nodes in the tree, so that is a large number of estimations being performed. Okay, 15,000 again. We run it again. There's slight variations in the speed time that depends on a few little things. 15,000, and it's again it's accelerated with results that are consistent with true with a 15,000 step tree, and I'm comparing with output or results that are established in the literature. Again, if we were to do that in more we could run it this way, 15,000. This again is the second part of the table 1 here, and I'm using these parameters or parameter values. B here is R negative Q. It's the cost of carry. So whereas here it's actually dividend in the dividend, here we have R negative Q. So a dividend of 7% and a risk-free rate of 3, that's consistent with having B equal to negative 0.04. Okay, so if I just run these all together, 15,000, 15,000, so 4 additional estimations, it won't be super fast, but it's not bad also. The results are relatively quickly delivered, and again I'm kind of getting consistency here in terms of the range of times involved. They're not always going to be exactly the same, but are fairly close in this instance. Okay, Another paper that I like a lot and is important for my own research is a paper by Callingham and Mutteraman, right? So this is for the European Journal of Operation Research, and they also deal with this issue in terms of the free boundary problem. We're looking at that. They produce results that increase accuracy and have high levels of speed, so they address this issue in terms of run times and accuracy. In this particular paper, for the moment, what I would like to address is just the output for the 10,000 step binomial tree. And so there's a range of parameter values reported in table 1 of that paper, and the X here denotes the asset price, T the maturity, R the risk-free rate, sigma the volatility, and then delta the dividend, and the exercise is constant at 100. So again, in Excel, I look at that again, and I take those parameter inputs and I put here. So basically I've copied this snippet of the table, and a few things pop up of interest. First of all, we have an extra decimal of accuracy, which is important. I inputted the same parameter values. This time it's for put options. It's American put options, and then the in terms of the row here, the parameters that we're using are consistent with the parameters here reported in the table. So for 10,000 step tree, again we can do 10,000 steps, and the results that I obtain 20, and 20 is consistent here. We can go again. Again, you notice that the speed is very zippy. There isn't a huge amount of latency in terms of estimation. 0936, 0936. Now I could increase a little bit we can put in, leave it like that, I guess, just to make it a little bit bigger. Go 10,000 again to compare results, 10,000. And again, what we're doing here is we're estimating the Cox-Ross-Rubinstein tree. We're using these parameter inputs, and the values we're getting are consistent with the values reported in the paper. So 8.9239, and that's what I have here, except this is 8, but the next decimal is 6, so next row should go to 9 anyway. One where our values differ are here in terms of, so maybe I'll just move the green a little bit here for the moment. This value here, with this range of values, right, what we're finding is the results that we obtained here in the table 1 not consistent with ours. Now I think that's just, if you put in 10,000, you can see here we're getting 1052. That's not the same as the 14.1740. And again, I suspect perhaps this should be 35% or perhaps 40%. And under those circumstances, the value reported here would be consistent with what we have. But the values we have here using this particular algorithm, again, where is that algorithm coming from? It's coming from the our paper, this paper, an efficient lattice search algorithm, and at the end of the paper, the last 5 pages, right, consist of code, VBA code that you can load directly into the Visual Basic Editor. And to run the Cox-Ross-Rubinstein tree, all you merely have to do is to copy the code here, load in, do a little bit of editing, and it should work without too much difficulty. Okay, so if we go back in here, the results, there's an inconsistency here between my result and result here. I was a bit concerned about that. So I went and got some code for Bjerksund and Stensland, and I actually have that in another video clip, but I'll leave a link below the video, and using Bjerksund and Stensland. Now we don't need these because there's no time step in Bjerksund and Stensland. It's a closed form solution. But if we take those parameter values that we have here, right, we get 1052 with Cox-Ross-Rubinstein using my technique, and using Bjerksund and Stensland 1048. This is just an approximation. The value here of 1417 looks too high. Okay, and again, this occurs a couple of times. Okay, so every second last time here we're getting those results, right? So again, if I copy this, copy and paste, okay, we find we're getting something similar here as well. So when I come down below here and do the same results, again, notice the speed here is fast. 10,000, 10,000, normally being done here quickly, right? Now we can take 10,000 and just drag it down and just see how quickly the estimation has been done. It won't be super fast because there's 1, 2, 3, 4. There's 10 estimations, I think, or 9 at least estimations that I'm running here. But it's not awful, and we're getting results here consistent with, if we, this 20.0108, the same as Bjerksund and Stensland. Same results, 2.88 is consistent, 2.4. The next value is consistent to 12.64, 12.64723, right? Consistent. When we go next one, it's not consistent, right? So at 10,000 steps, 11.21. This is 17.12, but there seems to be a pattern in the data here that every this fourth one, again, this value here, and the second last one, the value here is higher than from Cox-Ross-Rubinstein, and we can use Bjerksund and Stensland as a kind of control just to see. So these numbers look out of whack, but otherwise the numbers are the same. And okay, so the big benefit here is just speed, and speed also is being introduced here into the spreadsheet. So if we take the VBA code that we've developed using the efficient lattice, available in our paper, we are able to get 10,000 step trees and 15,000 step trees running at a fairly fast pace. In the literature, the holy grail is to get a closed form solution, right? So a lot of progress has been made in terms of developing a closed form solution for estimating the value of American options. And Zhu is probably the one that stands out in the sense that it gets an exact, or provides an exact solution. But even these closed form solutions sometimes involves using a Taylor series expansion, where perhaps you need up to 30 terms included to get this very high level of accuracy. And even no claims are being made here in that these models are fast. In fact, the reverse. Zhu, in a couple of emails exchanges that I had with Zhu, he mentions that the model is not intended to, in any sense, these closed form solutions are not intended to produce results at high levels of speed, and are not supposed to be viewed as in any sense enhancing the level of speed or acceleration. So in the next video, we're going to go back into the paper, and we're going to set up the code in the last 5 pages, and just demonstrate how from scratch you can run this accelerated CRR code.